Okay, I'll start off with, can you see the computer screen? I'll start off with any questions you happen to have on the homework.
This might be a better question for office hours, but
Okay.
how we use the delta method? There are two random variables.
Okay, so so the delta method, well, you'll use the sort of the fancy Pythagorean theorem. So, right, solve for f in 1b, and then you'll take the partial with respect to r1, square it, multiply it by sigma 1, well, s1 squared over n, take the partial with respect to the second variable, square that, put in the means, the data from the means, and then multiply that by s2 squared over n2, right? So it has two terms. I'll try to give you a slide during the office hours that shows how to do that. We talked about it probably first semester, right, in 564 when we did the central limit theorem. So it'll look like that. And C, there was a little bit of a confusion. So we can't really do the standard deviation of f. We can estimate the standard deviation. We can get the standard error by using the data that we have, R1 bar, R2 bar. The variance is from the two sets of observations. We can go from there. Any other questions?
Dr. Cho, just a general question. So does the delta method always give a better confidence interval than a bootstrap, or they can be really comparable to each other as well?
What should I say? If you have a small amount of data and a really skewed distribution, then the central limit theorem won't apply, right? The delta method assumes you can use the central limit theorem. I was going to give another example of the bootstrap, but I ran out of time. So that other example would help you understand the bias. And so the delta method has no hope of giving you the bias, but what the bootstrap can do is if you resample, then that resampling has a tendency to leave out outliers from time to time, and leaving out those outliers helps you compute the bias. That was the original use for the bootstrap. Mm-hmm. But and so the delta method's nowhere with respect to that. So but in the cases I give you just to get you off the ground, they're pretty comparable.
Okay, thanks.
Anyone else? Okay, away we go. Yeah, we'll have time at the office hours at 2. If my internet survives this afternoon, I had a silly experience with the internet. They told me to unplug my Nova and replug it, and then unplug my a computer voice and unplug my router and replug it. And so I did all that stuff and called back, and then they said, "Oh, your system's down." So I said, "Well, why didn't you tell me that the first time?" So anyway, so far it's been working fine today. So we'll do full screen. So we had a fairly theoretical introduction to how chi-square works with Wilks' theorem, and there's a lot of magic that goes on, right? The Fisher information matrix comes and goes. We see it both in the terms of it's showing up with respect to the central limit theorem, and it's showing up with respect to the law of large numbers. Right, the central limit theorem gives us the variance version of how you compute. Oh boy, how many moments need to exist? I think the central limit theorem. Okay, so Nathan asked, how many moments do you need? So the bootstrap is embedded. That is, its asymptotics works is embedded in really the central limit theorem, right? That is. The Glavinko-Cantelli lemma, if you've heard of it, tells you that you get a convergence of the cumulative distribution functions. But if you don't have some variance structure behind that, you don't have a rate of convergence that you can really count on. So I would say a couple of methods in the background are what are needed to get the bootstrap to work. Okay. So I'm going to look at contingency tables today. I'm going to look at them in 2 settings. The one setting is where we use the chi-square statistic, and the other setting is an alternative that shows up when your tables are a little bit small, and it's embedded in the hypergeometric distribution. It's called Fisher's exact test. is there a cool theorem indicating that, oh, you might get a rate of convergence if you had 1 plus epsilon moments. That's true because you would, but I don't know that exactly, right?
No, it is true. In Casella-Berger, there's a discussion of it in one of the miscellanea. So
I see.
it's worth taking a look. It's
Okay,
cool.
So if you have more than one moment, yeah, then you can say something. But it's hard for you to say. Can you say something about the distribution of the errors? I have to look at that, right? Because you would be in the domain of attraction of some, have to be in the domain of attraction of some infinitely divisible distribution, and I have to think about that. Okay, so contingency tables are also called two-way tables, and they're also called cross tabulations, and it's the most typical way that you see of frequency distributions between two categorical variables. So a typical letter that we use is R and C, R for rows and C for columns, two factors which we call A and B for an experiment. So it gives you R categories, which I'm going to call A1 through AR for the first factor, and then C categories B1 through BC for the second factor. You can actually do three-way tables and four-way tables and so on. You'll need a special, you'll need to download some software to help you analyze that, or if you can write your code from scratch. But two-way tables contain a lot of the essential information that you need to go forward. You can see how the calculus would go for higher than two-way tables. So let OIJ be the number of occurrences or observations that are simultaneously in both the I category for A and the J category for B. And then you organize it in a two-way table, and there are all the observations that you see in all the tables. And we have a tendency to look at the marginals. And so you see an O1 dot for the first row, an O2 dot for the second row, and an OR dot for the rth row. And then the same thing along the columns. So you sum over the columns, and you have a dot 1, a dot 2, a dot C, and so on. And then the total numbers in, I guess it could be called O double dot for the total number of observations. So I'm going to look at, I'm going to look at blood types. Oh, we talked about blood types. I'm going to look at the RH factor, right? So the RH factor is it's a blood group antigen that sits on the surface of a red blood cell, and there's only one of them, that matters, but that one of them can cause serious problems, I guess, with the second child if there's an incompatibility with respect to the father and the mother. And that second child is what's necessary because the immune response happens after the first child is born. And so they're called positive or negative, and they refer to that one antigen. I think it's called antigen D. And so if we collect the data from 300 individuals from a large population, I got this from a textbook I was unable to get online yesterday to get you a sort of a more fun or interesting table. Here's the table I came up with. So you can see O is the more, A is the most common blood type. And so we have 244 that are RH positive and about a quarter of that many that are RH negative. To give the 300, you can see they're distributed among the four groups, many more in O and A, somewhat less than in B. And in this group, that should be O, A, B, and AB. So it should be O, A, B, and AB. How did that happen? Okay. So the null hypothesis is we shall consider that the factors A and B are independent. That's the question. So is blood type and RH factor independent? So here are the parameters. Pij is an individual that's simultaneously a member of category AI and category BJ. And so then you have a parameter space, and that parameter space is a set of a matrix of numbers indexed by the rows and columns so that they're non-negative and add up to 1. And we can write the marginal distributions as Pi dot, just like we did with the OI dot. So that's the sum over all the columns to give me the marginal for the ith row. And I could do the same thing. I could sum over all the rows. Sum I goes from 1 to R of Pij to give me the marginal distribution P dot J of an individual being in category Bj. Okay, and so then the null hypothesis for these two-way contingency tables is one of independence. So it says that the probability that you're simultaneously have row category I and column category J, Pij is equal to the product of those two, Pi dot and P dot J. So that's, you're testing for independence, so that's the null hypothesis. The alternative is some value of I and J is different from what Pij is. Okay, so for the parameter space theta, the big parameter space, you have R cross C probabilities. So that's R times C numbers, but you have a single constraint that their sum is 1. So the dimension of that space is RC minus 1. So in the example I gave you above, there are 4 rows and 2 columns. Is that the way I did it? 4 columns and 2 rows. So the number of, so R times C is 8. I subtract 1, I get 7. And then the null hypothesis, you have R row probabilities Pi with the constraint that the sum is 1, so that's 3. And then you have column that's the rows, 2 rows, so that's 1. You have 4 columns with a constraint that the sum is 1, so that's 3. So you have 1 plus 3 is 4, is the dimension of the null space. And so R minus 1 plus C minus 1, and then the difference in the dimensions is RC minus 1 minus the dimensions of the null space, which is R minus 1 minus C minus 1. And then I'll do some algebra on that to get RC minus R minus C plus 1. And I can factor that into R minus 1 times C minus 1. And that's probably the expression that you've seen the most. Later on, when we look at this a little bit more practically, then I'll give you sort of a heuristic so that you can remind yourself why it has to be that. Okay, so the data are just numbers that fill up that matrix of observations, the OIJs. And so the number of observations that lie simultaneously in category AI and BJ. And I won't go through this, but you can check that those are the sufficient statistics. You don't need to know individually which individual belongs to which category. All you need to know is the number of people that belong to simultaneously the categories I and J. You just need to know the number of people that are O positive or AB negative and so on. So you want to maximize the likelihood, so that the product over all the columns and all the rows of Pij to the number of observations you have in there. So you can do the same thing that I did last time with the Lagrange multipliers for the goodness of fit. Now you have a double sum. The sum has to be 1. You set up the gradient observation that you need for Lagrange multipliers, that the sum of those probabilities has to be 1, and you get the maximum likelihood estimate that you expected to get, that the maximum likelihood estimator for Pij is just the fraction of observations that happen to be in that cell, right? So it's simply the fraction of observations that are in categories AI and BJ, and I'm reminding you is the total number of observations. So that was easy. Now you have to substitute that back into the likelihood function, or at least the log likelihood function. So the log likelihood function would be just the sum on I and J of Ni times log of Pij, but I'm going to substitute for Pij its maximum likelihood estimator, which is Nij, the number of observations divided by the total number of observations. Okay, now we have to maximize under the null hypothesis. So in that case, P naught Ij is Pi dot times P dot J. And so if I look at the maximum likelihood, the likelihood function under the null hypothesis, then I have again the product over I's and the product over J's, and I replace Pij with its property under the null hypothesis, which is this product Pi dot times P dot J to the power Nij. And then since I have a product of things that are raised to an exponent, I'll factorize that to Pi to the power Nij and P dot J to the power Nij. And then I can multiply that as a product of probabilities that depend only on I, right? That is, I can sum over the I's, and I could do only the product of the probabilities that depend upon J. Right, so you, and now I have 2 maximization problems, one for Pi dot and the other for P dot J. And so again, you can return to the Lagrange multiplier strategy for each of these separately. you can determine their maximum likelihood estimates in exactly the same way. And you get that PI dot is NI dot over N, and P dot J, excuse me, is N dot J over N. So now I have all my maximum likelihood estimators. I now have to stick those values into the log likelihood that under the null hypothesis. And so, oh yeah, I guess I should go back and say that now my maximum likelihood estimator for P hat naught has I jth entry N sub I dot over N times N sub dot J over N. Okay, so now I substitute that back into the log likelihood function, and I get the sum over i's and the sum over j's of nij, and now I have the maximum likelihood estimate under the null hypothesis. Okay, the likelihood ratio says statistics say that we should look at the ratio of the situation under the null hypothesis and the alternative, and I could write that down by subtracting. So the log likelihood ratio is going to be the log of the maximum likelihood of the likelihood under the maximum likelihood estimate under the null hypothesis minus the log of the maximum likelihood estimate overall. And if that number is sufficiently negative, I'm going to reject. So I'm just substituting in what those are. Both of them had a factor of Nij, so I can put that to the front. Oh, the second one, I should have stuck with the natural ln, so I don't know why I went to logs, but so it's going to be the log of the maximum likelihood estimator under the null, which is Ni dot over N times N dot J over N minus the maximum likelihood estimator under the overall, so that's Nij over N. And then I'm going to do some simplification that looks a little bit tricky at first. So you'll notice that the first logarithm has an n squared in the bottom, and the second logarithm has just an n in the bottom. So I could divide each of those logarithms by taking out a factor of n and subtract the log of n from both of them, and so they disappear since I subtract the difference of the difference of the same number is 0. So then I get Nij, the log of n dot I, Ni dot times N dot J over N is the log of Nij. And for those of you that are used to the ideas of maximum likelihood, then you'll recognize those factors. If you don't, we're going to put them in a using notations a little bit more familiar to you. So the way it's typically written is Oij for the number of observations times the log of Eij, and I'll have to explain where that comes from, divided by Oij. Okay, so Eij is going to be that expression. Well, okay, Oij is easy. It's just Nij for the number of observations in the ijth cell. Eij is going to be, at least informally, you take the number of observations totally, you multiply it by the fraction under the null hypothesis, multiply by the maximum likelihood estimator there in the ith cell times the maximum likelihood estimator in the jth cell. So under independence, that's the expected number of observations you would see in the nth cell, in the ij cell, excuse me. Okay, and then one of the n's cancel, and I get Oi dot times O dot J over N. So that's what the Eij's are. And now you multiply by -2 to obtain the desired G squared expression for the likelihood ratio statistic. And I didn't write it down, I should have, but the other thing that you can do is you can write it down as this sum of Oij minus Eij squared over Eij, just like we did for the goodness of fit by using the second order Taylor series approximation of the logarithm about the number 1. And then that will match in some sense the same kind of second order Taylor approximation that we did in the proving of the chi-square statistic. And it's also the one that Galton used to create the chi-square statistic. And it has, at least from the circumstances of a century ago, the nice ability that you can compute it by hand, whereas you have to have a logarithm table to compute this by hand. And I am old enough to remember logarithm tables. I don't know if I have one around here, but I'm old enough to remember it. Okay, so for the data on blood type, we find the expected table. So there's my table, and I put in the marginals, right? The total number of people with type A blood is 95, and the total number, here I have the tops correctly listed. Total number of people with AB blood is 61. The number of RH positive people is 244. And the number of RH negative people is 56. And you can check the row, the sums along the columns or the sums along the rows, and you can get 300 both times. That's one thing I do to check my arithmetic. And so you want to now fill in the table according to the little strategy that I told you about. So to do the E11 category, you look at the row 1 column sum, which is 244, times the row 1, that's the row 1 row sum, which is 244 times the row 1 column sum, which is 95. You multiply those two together and you divide by 300 and you get 77.27. So that's the number you would get if the null hypothesis were satisfied exactly. And I could do the same thing with the other 3. Then you have your choice to do the next one. You could do the same thing by multiplying 56 by 95 and dividing by 300, or you can recognize that the sum has to be 95, and there it is. I did check just to be sure, and then you can fill in the others. And you can check that the row sums and the column sums in this expected table have marginal values that are exactly the same as the one in the observed table. So now you can then compute the chi-square statistic by hand. Okay, to determine the number of degrees of freedom, I gave it to you one strategy, but the one that we typically use to help ourselves think about it is start with a contingency table with nothing inside of the table, but the prescribed marginal values. So let's pretend you have that table. Now start filling in values, and then and you can fill in a certain amount, and those would be sort of your degrees of freedom until you can't fill in anymore because the constraints of the marginals dictate what the values have to be. So the degrees of freedom can be determined by counting the number of values that we can place in the table before all the other remaining values are determined. So you can fill in the first C-1 values in each of the rows, top rows, because if you leave out the last column, I mean the last column in any of the rows, then you can fill in that value because the row sum is determined. And then you get to the, and if you've done that for every row, once you get to the last column, everything has to be filled in because you have to match all the column values. So you can fill in C-1 values in each of the R-1 rows, and then after that, you're done for. You can't do anything more than that. So if you do C-1 times R-1, that is one way to think about the degrees of freedom. That might be slightly easier to think about than the dimension of theta minus the dimension of theta naught, which is the way the theory sort of prescribes it for you. But this is in an elementary class. This is typically the way they describe these things. Okay, so for the chi-square statistic on blood types, the number of rows was 2, and the number of columns was 4. So 2 minus 1 times 4 minus 1 is 3. Okay, so R handles this for you. So I just created a matrix of the blood types. The way R works is it fills down columns. So there are the data, just written in R. And you do chi-square test blood, and out gives you an answer. Calls it Pearson's chi-square test because it uses the O minus E squared over E rather than the OIJs times the logarithms. I don't know of a simple R command that does that kind of chi-square test. The chi-square statistic is 8.6. The degrees of freedom is 3, just like I promised. And the p-value is, it's lowish, 0.035. But so am I really willing to say that it's not independent? I'm a little nervous. I would like to have more data. What I didn't get to cover in this lecture that I thought about is how do you do a power analysis with respect to chi-square statistics. So I'll say a little bit about that, but I won't end up lecturing on it. So just like there's a non-central t statistic that helps you compute the power for a t distribution, or the power in case of a t-test, there's also a non-central chi-square statistic, which looks at the distribution of the chi-square where the variance is still 1, but the mean is shifted. And if you think about it for a minute. It's going to depend upon the sums of the squares of the means as the quantity, and then you try to take that into, let's say, this two-way table to try to get what deviations that you need to see in general from the two-way table to say that you're really seeing a significant difference. That's sort of a complicated question. And then there is actually a power.chi_.test command that helps you do that. And there is a PWR R package. There's a bunch of those power analyses for you. Okay, we can also look at the residuals. Again, that's a way to help us try to see what was going on. And so the residuals are just the square root of the entries in the table where I take the square root, the version of the square root that has OIJ minus EIJ, right? You have two versions of the square root that you could pick, but this is the one to pick. So sometimes it'll be positive if observed exceeds expected, and sometimes it's negative if expected exceeds observed. So then I'll save the data and I'll build the residuals, and you can see in the table the residuals for type B blood in the Rh positive people is positive, and in the AB blood it's positive, where it's fairly negative for the other two. And you can see the residuals look higher for the Rh positive than the Rh negative. I think it has to do with the fact that there's many more observations in that group. Okay, so I'm going to show you two horizontal chi-grams that help you summarize the residuals in this case. So I created a little vector called residuals. It took all the residuals of the blood test, and I gave them names, A, B, and O. And then I created a graph. So I want a graph that has 2 rows and 1 column. And then I just make 2 bar plots for the positive one and the negative one. And there they are. So, so you can see that if you have a positive residual for one of them, you almost always have a negative residual for the other. And that the Rh negative ones are somewhat exaggerated in terms of their z-scores because they have a smaller number of observations. So that's a way for you to sort of communicate how the Rh factors differ between the two groups, which one it impacts. It may have a positive correlation, which one it may have a negative correlation. Okay. Now you can't always use a chi-square test because a chi-square test is based upon the central limit theorem. And the central limit theorem is based upon your ability to use a normal approximation. So there's an old criterion due to Cochrane that requires that no cell has count 0 and more than 80% of the cells have counts at least 5. And in fact, if you look at the chi-square test, then it will give you that complaint. Maybe I'll show you that. If this does not hold, then the Fisher exact test uses the hypergeometric distribution, or a generalization of that really uses multinomial coefficients rather than binomial coefficients. So it uses that directly rather than the normal approximation. It's much more computationally intense, but I'll go over exactly how that works for you in the next few slides. I'll do it for a 2x2 table because that will use binomial coefficients. If you wanted to do a larger table, then it would depend upon multinomial coefficients. So here's the table filled out for a 2x2 table with the number of observations and row and column totals. So I've ended up using the Fisher exact test pretty regularly because when I was looking at these data on mutations for sodium channel mutations, a lot of times my tables were pretty small, but my data were fairly clear. Sometimes, you would have zeros in the table. So the question is, how unusual is a 0 is part of what we end up asking ourselves. My daughter she worked with honeybees, and she uses she always used the chi-square test, and then she got a referee's report that said you can't always use the chi-square test. So what she did was, in almost every case, her data was of marginal size, the number of honeybee colonies that she was able to look at in order to use the chi-square test. So she would do both tests to show that they gave comparable p-values. And we'll do the same thing here. We'll use both tests. We'll see the p-values are comparable, and then your decision or your conclusion based upon those things won't differ depending upon which test you take. So the idea between Fisher's exact test is begin with an empty table with the marginals filled in, and the null hypothesis of equally likely outcomes. That is, I'm going to make all the ways that I can fill in B1 and B2 so that the marginals give me the same things, have equal likelihood. And what I'm going to do is I'm going to turn mark and recapture on its head. Typically, mark and recapture is we don't know the number of individuals in the population. We don't know n. That's the goal, to find this out. What I'm going to use is I'm going to use mark and recapture to see, did we sample in such a way that the individuals that we got in the recapture are representative of the distribution overall. So to see that we did sort of had good fidelity with respect to the requirements for mark and recapture. So normally the goal is to find n, the total population. In this case, I'm going to assume that the population size is known, and I'm going to see if I again have a good mark and recapture method, because if that's the case, then the individuals that are in the two captures are independent. Okay. So we're going to test the independence now. So I have 4 cells, and I'll give them names. So A1 is an individual that's in the first capture and thus tagged. And A2 is an individual that's not in the first capture and thus not tagged. So the A1s are the question, were you in the first capture? For A1-1, the answer is yes. For A1-2, the answer is, for A2-1, the answer is no. Or for A2, the answer is no, excuse me. And then the B1s are questions about the second capture. So for the second capture, either you were in there or you weren't. So that's what B1 and B2 are. So that describes sort of the whole universe of things. Okay, now let's look at the point of view of the A classification. So A1 dot is a number that have the A1 classification. That's the number of tagged individuals. So how can this be accomplished? Well, there were n individuals in my population, and so I'm going to choose from those n individuals O1 dot that will get tagged. And so that's this binomial coefficient n choose O1 dot. Again, if you had more than 2, it would be a multinomial coefficient, but we'll stick with binomial coefficients. And I wrote it out because it's going to be important soon to see the whole set of products written out. Okay, then O2 has to have O2 dot has to have n minus O1 dot, right? And they have the A2 classification because either you're an A1 or an A2, and that has to add up to n. So either you're tagged or not tagged. Okay, so now from the O.1 category that belongs to B1, that is individuals in the second capture, of those, O11 also belong to A1, have a tag. So you look at the second capture, how many are in there is O.1, and then you ask yourself, how many belong to the first capture, have a tag? And again, that's going to be a binomial coefficient, O.1, which is the number in the second capture. Choose the number that have a tag, and I'll write down that binomial coefficient with factorials, right? Because we know that A11 plus A21 is A.1. Okay, now we're going to go to O.2. Those are individuals that belong to B2, that is individuals not in the second capture. O12 also belong to A1, that is have a tag. So these are individuals not in the second capture, but having a tag. So, so that's O.2 divided by, choose O21, and there's the multinomial coefficient for that. So what I did is I built the multinomial coefficient in 3 pieces for you, as we saw last semester. So under the null hypothesis that every individual can be placed in any group provided we have the given marginal information, that probability is just a hypergeometric function. And there it is from each of the 3 pieces that I have. And now I'm going to write them all out. So it's O.1 divided by O11 factorial, O21 factorial. That's the first term. And then it's an O.2 factorial times an O12 factorial times O22 factorial. And then I divide that by n factorial over O1 dot times O2 dot, both factorials. And then I'm going to rearrange things. And if I do that, right, the O1 dot and the O2 dot stay on top, and then there's an O dot 1 and O dot 2 stay in the top, but there's an O1 dot and an O2 dot factorials that will move from the denominator in the denominator up to the numerator. And then all the individual terms, O11, O21, O12, and O22, and N, all move to the denominator. So that's the expression, all 9 terms. But what I want you to see is that expression is symmetric in the row and column variables, right? So if I did everything from the perspective of the A, if I did everything from the perspective of the B's, then you would just replace the 2 dots with 1 dots and the dot 1s with the dot 2s, and everything would stay the same. So it's symmetric with respect to the row and column variables. So it didn't really matter which order that I picked in order to decide on how to build this Fisher exact test. Okay, so if we had derived the hypergeometric formula from the point of view of the B classification, we would have gotten exactly the same formula by that symmetry. Okay, so to do the test, you have to rely on software, and this is what the software does. It computes the hypergeometric probability over all possible choices for entries in the cells that give the marginal values. That's not completely true. If the numbers are small enough, then it can compute that whole hypergeometric function for you. If it is, it's easy for you to get in the millions of possibilities, or many millions of possibilities, for what you could use to fill the cells. And in that case, what R does for the Fisher exact test is to randomly pick strategies that fill in the probabilities for those cells, and then keep track of all of those to see how often they occur. And it compares that to the one that you saw in the data. So rank these probabilities from most likely to least likely. So you can either do it for all of them, which would be the exact test, or you could do it for a sample of them that are randomly chosen. Then you rank them. And then for a one-sided test of 2 rare, the p-value is the sum of the probabilities of the rankings lower than that of the data. So that's how it works. And I said you would never want to do that by hand. You might be able to get away with it with hypergeometric with 1, but it would be still quite a chore. Okay. And I said a similar procedure applies to provide the Fisher exact test for R by C tables, except you would have multinomial coefficients all over the place rather than these binomial coefficients. But in principle, it's the same kind of idea. So let's test the idea of mark and recapture. I'll look at a small population of 120 fish. So for example, I could sort of test the fidelity of this by having a known population and then train people on how to do mark and recapture and see how good their ability is to make this independence assumption that's part of the Fisher exact test. So the assumption is that each group of fish are equally likely to be captured in the first and second capture, and that the 2 captures are independent. Okay, so typically what we say is we give the number that are tagged and returned to the pond. So I'll assume it's 25 in this case. And for the second capture, which we again determine 7, we have a size 30, and of those 7 are tagged. So that's what we typically see. And so that information will be given in the table below. So there's the 7. Let's do it in the order I did it. So there's 25 that are in the first capture. So that's the first row sum. There is 30 in the second capture. So that's the first column sum. And then there's 7, right, that were tagged. So 7 that were tagged means that it was in the second capture and in the first capture. Okay, so that now, and then I know there's 120 overall. So once I know those 4 things, I can fill in the rest, right? Because I need 18, not in the second capture, but in the first capture to get a sum of 25. I need 23 in the second capture, not in the first capture, get a sum of 30. Okay, and then I need 90, not in the second capture, get a sum of 120, and then I can fill in the 72 in any number of ways, and the 95, I guess, in any number of ways. Okay, so the Fisher test is, again, you put in the matrix. I have 2 columns, so I just put in those 4 numbers. And then you just have to write Fisher.test on the data, and it gives you a test for count data. And so the p-value is 0.8. So you can't really say much is going on here. If you have a 2x2 table, then you have an odds for each of the columns. And you can ask yourself, what's the odds ratio? It should be close to 1. That is a ratio of the A11 to the ratio of O11 to O12 should be about the same as the ratio of O21 to O22. And it can build a 95% confidence interval for that. That is, it looks at all of the possible combinations and it tells you what ratios, it builds a 95% confidence interval based upon those ratios and what you got from the data. So the odds ratio for my data is 1.21, and so that's close enough to 1 for me to say that that I can't reject the idea that it's exactly 1. For a larger table, you won't see odds ratios. So the Fisher exact test shows a much too high p-value to reject the null hypothesis. Okay, and so I actually, see, I did it. For the blood data. So here's the blood data again. And then I did it. Oh, and then if you do the Fisher test, the p-value is 0.03662. And you see it doesn't give me an odds ratio because it's not a 2x2 table. I did it again for no particular reason, but if you do the chi-square test, which is what I did earlier in the lecture, then you get a p-value of 0.035 as opposed to a p-value of 0.036. Oh, I know why I did it more than once. Because if you don't say anything, it will try to automatically give you, it'll automatically, if the cells are too big, it'll automatically pick a randomization procedure in order to compute the p-value. And if you use a randomization procedure to get the p-value, then you won't get the same answer from one time to the next because of the randomization. And so so I did it again, and I got exactly the same answer, at least the same answer to 5 decimal places. So my guess is for this 2x2 table, since it uses a hypergeometric distribution, one hypergeometric distribution, then it's able to do everything. And that comes from the fact, for example, in the chi-square test statistic, the number of degrees of freedom in a 2x2 table, pardon me, is 1. And so you only need to really fill in one cell and use that one hypergeometric distribution to do that. If you go back to the chi-square test and you look at a 2x2 table and you were to work through it all, you would see that you get exactly the same as the 2-sample proportion test, a 2-sided 2-sample proportion test, or you get the square of that since it's a 2-sided test. And the chi-square statistic goes with that. So it takes you back to something that we've seen before. Okay, that's what I have to say today. I'll try to get a homework assignment to you soon that gives you information on some things to do with the chi-square test. I'm going to try to get out some information soon so that you get ready for the test next Thursday. So you'll have some ways to focus your activities. Next Tuesday, I will probably do a fairly theoretical lecture on how analysis of variance gets put together. And then the last lecture, if you want to listen to it, I won't give homework assignments on either one of these. If you want to listen to it, then I'll give a very practical thing that ties the theory of analysis of variance to its practical use. So that's how we'll finish up the semester. Any questions before we close off for the day? Okay, I hope everybody's doing well, staying healthy, keeping your spirits high. It's all pretty important right now. Most people I know are doing well, but those people who aren't doing well are really having a tough time of it. Okay, so we'll see you at 2 o'clock, some of you.
Thanks, Joe.
Oh, you're welcome.